So this last unit 9 will be about the range minimum query problem. And I'll tell you what that is. It might first sound a little far away from what we previously did, but then you will rediscover that it actually solves a gap that I'll have to leave earlier in the class. And it will have some very elegant and beautiful solutions. So let's see what this is all about. I'll talk about the introduction. We'll come back to the funny headlines later. So what is the range minimum query problem? It's a very fundamental and simple problem, simple to state. You're given an array of numbers, like so often in this class. It's just a bunch of numbers. And what you would like to do with this is, given a range like this one, going from 7 to 15, you would like to find where in that range is the smallest element. So there's one number here, number 2, which is smaller than the others. There's a tie, which we'll come back to, and you report the position of this minimum. That's all. Now, it's a very boring problem unless you're given this array up front and you can have a look at this array before you have to answer those queries. And this is the rule here. This is the game. So you get to look at this array. You can study it in detail. You can pre-process it, and you can also store auxiliary information. And then at query time, I'll just give you a range, 7 to 15, and you tell me as quickly as you can where the minimum is. Two little details that are important, but might not be might not be something you think of if you first hear about this problem. What we report is the index of the minimum, not its value. That will be important just at the very end. Most of the module could come, most of this unit would work the same way if it was the value, but it will eventually be important. And the second thing is we report the leftmost position in case there are ties. So here there's 2 occurrences of the 2, which is the minimum in this range. And we decide we want the first one. That's it. Very simple problem, very simple to state, and I should save this, yes. A very simple problem to state, but it has a very rich solution space. Before we come to that, I want to be 100% sure that you know what we're doing. So please head over to Pingo and answer this simple question. I'll give you the usual 2 minutes. Okay, I have to refresh here first. So now the question is live, and I'll leave the slide on here for some more time because the question doesn't have a copy of the array. So a simple question, no tricks. I just want to make sure that the definition is very clear to everyone. Yeah, a good idea is if you're done to post in the live chat, we can play that game again. I guess that's a fairly simple question, so I would head over now and stop the question then. Okay, time's over anyways. It's slow to navigate here. All right, okay, the view is not very helpful. Clearly most of you answered 1, a few answered 4, and well, a few other, which might be other ways to express the same thing, but so let's do this quickly. 1, 6 is the range, and endpoints are included, so 1 up to 6, this is the part of the array that we're looking at. Now the problem's called range minimum, so we find the smallest in there. There's actually 2 copies. Now the second part was we report the position and not the value, so the answer is 1, which most of you have answered. So we know what the problem is. We know what we're trying to solve. Let's try to solve this problem. A few more remarks about how we frame this. First of all, I treat this as a comparison-based problem, which means the algorithms that we'll use, like the sorting unit also had the same assumption for most algorithms. The algorithms will only compare 2 elements. One can be smaller than the other or bigger, but we will not try to use the numerical value of these numbers. That's just an assumption to make parts of the theory cleaner and easier, because then the values of those numbers don't matter, only the relative order is important. And that helps us reduce the space of possible inputs also. Unlike many of the algorithms in this class, there's actually 2 things where time is of interest, and that's the first is the pre-processing time, which is the time you spend before any queries are answered, so the time to look at the input array and save some notes about it. And then there's query time, which is the running time of answering a single query. And both are important. It's not very interesting to have a solution that's great in one metric and totally poor in the other. So what we'll do is we'll just write both of those in angle brackets to have a shorthand to say there's a certain pre-processing time and a certain query time associated with a given solution. I should add, we're also interested in the space. It's not our primary concern in this module, but in principle, we spent some time on arguing about space, in particular for suffix arrays versus suffix trees and these things. The interesting observation here is that the pre-processing time is always an upper bound on this, because we cannot use we cannot sensibly use more space than we spend time during pre-processing, because we would have to write that data eventually. And it will be the case that for the interesting methods that we'll look at, the pre-processing time is actually the same as the space. So computing these things that we will store will be very cheap, but the amount of things we want to pre-compute will drive the time and the space. So for this problem, space usage is not a separate concern. It will be essentially given by the preprocessing time. So I want you, before we get started and before I show you solutions to this problem, I'd like you to think about what you expect, what you think is possible, maybe even have an algorithm in mind, what we can do. So think about what solutions you expect. And the question on Pingo that I'll start also allows you to send multiple answers. And the reason is there's multiple solutions to this problem. And there might be a trade-off between preprocessing time and query time. So it's not necessarily a single answer. So take a minute and think about this. The Pingo question is live now. So take a moment and think about this, what you expect. So you can send in both things you already feel how you know how to do. That's great. Or things where you just from your gut feeling think that might be what we're going for. As always, if you have any questions while I'm talking, while I'm presenting things, post them on Slido. I will eventually get to see them. Okay, thanks, Ben. Seems Pingo is not 100% intuitive in terms of adding multiple answers. Don't worry so much. This question is mostly for me to see what do you think intuitively is the answer here. All right, I think 3 minutes was ample. I'll stop the question now. Just see what we've got. Okay, I guess my format was a little confusing. I would have expected answers like this, where you have preprocessing time and query time. That sounds reasonable, actually. Oops, what happened? Okay, there's an interesting mixture of different answers. All right, that's interesting. Let's head back. We'll come back to solutions to this problem in a second, and I will also show you some that are definitely very, very simple. But before we get to that, I'd like to start motivating a little bit why this problem is interesting. And it was just tempting to add this subsection. You definitely know these three. Not sure if I wanted to ask you if you know the last one, but now you also know this abbreviation. There will be lots of abbreviations floating around in this chapter, but we will not usually need all of them. Recall what we did in Unit 6, the text indexing unit, where we talked about suffix trees and suffix arrays. That was one of the slides from back then. which was about this longest common extension problem, where you're given a string, a text, and you'd like to answer these types of queries. Given 2 positions in the text, what's the biggest number of characters that I can read from that position so that they are the same at both positions in the text? So, right, I usually drew this picture. There's an I and a J, some position, and then we ask how long is this part that we can put here so that they are the same. How many characters can I read starting at I and J so that the substrings here are the same? We talked about this extensively in Unit 6, and in particular we connected it to the suffix tree. So here was the example. And well, we figured out any of these starting positions is actually the starting index of a suffix. So there's a leaf associated to that suffix. And to find the longest common extension, say of 5 and 1, we would find their lowest common ancestor in the tree. So this node, and then it's the string depth of the lowest common ancestor. So LCE was longest common extension. LCP was the longest common prefix. That's what occurs here. And then string depth of the lowest common ancestor. Those are all the abbreviations that appeared here. That's how back at the time we solved this problem. And then I told you there's a magic box that we did not look into that solves this problem for us with constant time at the query. So given some pre-processing time, which was linear in that case, that's what I claimed at the time, we can do the lowest common answer queries in constant time. And then inserting this into the previous data structures and using suffix trees, we could get a longest common extension solution in the best possible time. And then we used that for the kangaroo algorithm for inexact matches, and so on and so forth. Now, we then went on to talk about suffix arrays and ditch all this tree, the suffix tree, altogether. And a comment I might have made at the time but didn't stress so much: the longest common extension problem can also be expressed in terms of the enhanced suffix array. And here's how. I might have to zoom into the pictures a little bit. I just want to show you the simple formula first. If you want to find the longest common extension of 2 positions in the text, so again, the picture from before, there's an I, there's a J, and I'm asking how much can I start reading here so that these 2 strings are the same. Then I claim I can find this by using a range minimum query on the LCP array and using those 2 indices. Oof, that's a few levels deep, so let's try to go a little bit into this. So first of all, why could it make sense that it has something to do with LCP? Well, that's what we've already seen before. We know that LCP is the longest common prefix of 2 adjacent suffixes in sorted order. So remember, the suffix array gave us the suffixes in sorted order. Here L is the suffix array, and R was the inverse suffix array. And if I have 2 suffixes that are adjacent in this sorted order, the LCP array would directly give me the length of the longest common prefix of those 2. That's the easy case. That's if I'm interested in the longest common extension of 2 positions so that the suffixes there are adjacent in sorted order. Then I have already pre-computed the answer in the LCP array, which is also here. Now, what happens if I'm interested in positions that are not adjacent? And let's use again. So before we had the example here, I took positions 1 and 5, the suffixes starting at positions 1 and 5. Let's try to trace the same example through this here. For that, I have to go over here. These are the suffixes at position 1 and 5. This starts at position 1. This starts at position 5. Now let's do that again. I want to know what those two have in common. What's the longest common prefix of those two? I know this is easy to do by just looking at the strings. The answer should be just A. But this is not how a data structure would do it, because that could be slow. You might be forced to scan the entire suffix. Instead, what we'll first do is we use the inverse suffix array, which takes us to the right to the sorted picture. These are in text order. We need them in sorted order for the LCP array. If we go to the right, the 1, R says, goes to number 4, position 4 in the sorted list. And R says 5 is actually number 1 in the sorted list. So we're looking at these two, and of course, these are the same strings, right? It's still A-ban and Anana-ban. What's the longest common prefix of those two? Now we're in the sorted picture, so we can move back over here. So we found 1 and 4 are the positions. Now I didn't include the positions in this picture. I should have. The indices are 0, 1, 2, 3, 4, 5, and so on. Now we're looking at position 1 and 4. And here the LCP array starts at 1, 2, 3, 4, 5. Now we're almost there. It says we should look in the LCP array between those two, which is to say in this range, in that little subarray of the LCP array. It starts at, well, 1 after the position of one of the strings, which is 1, and then means it starts at 2 in the LCP array, and it ends with the position of the second string. That's it. The LCP array in that range is 1, 2, and 3. So the range minimum query is 1. Or, well, it's... okay, you caught me. Here I actually mixed things up. It should be LCP of this. Because, as you might remember, the range min query returns the index and not the value of the minimum. But the longest common extension is really the value. That's fine. We just take the index that we get out and read the value in the LCP array at the appropriate position. So the range min query here that we're looking at is from 2 to 4. And the value, the return value of RMQ is 2 because that's the position where the minimum is. And then, well, in our case, LCP of 2 is 1. And that's the right answer because the strings we started with, Anana-ban and A-ban, they just have a single letter in common at the beginning. So that's how this works. I hope that example helped to clarify this connection here. So that was a long story, but it just means that any solution we can find for the range minimum query immediately gives us a solution of the same quality for the longest common extension problem. The reason for that is that all the other components that make up the longest common extension data structure can be computed in linear time. So they don't blow up the preprocessing above anything. And linear time is clearly the best you can hope for if the preprocessing is doing anything. It has to read at least the input. All right, so we understand why range min queries, this fundamental and simple problem, finding the minimum in a range of an array, how that connects to a problem that we already studied and that we found is useful for all kinds of string algorithms. At first, those two problems don't look like they're related, and the range minimum query problem is so fundamental that it might be unclear what the motivations and the applications are, but here's one, and there's actually many others. So it's a building block that pops up in different places.